This is Dr. Greg Hunter from the University of Technology, Sydney. This video presentation demonstrates a new control method called feed-forward torque control, originally developed for permanent magnet synchronous motors but applied here to hybrid stepper motors. The new control method provides servo performance at all motor speeds without rotor position sensors. This is the block diagram of the new feed-forward torque control method. Only the torque controller is shown. Speed and position controllers can be added as required. The feed-forward block calculates the motor voltages directly from the D and Q axis command current values using estimates of the motor electrical parameters. These voltages are converted to pulses by the pulse width modulator for feeding directly to the motor windings. The load model block calculates the required rotor angle and rotational speed from the Q-axis command current using an approximate mathematical model of the load. This block eliminates the need for a position sensor. Only a simple load model is used, which only needs to know an approximate value of the load inertia. The motor currents are measured, then converted to the D and Q axis components in the alpha beta to DQ block, using the rotor angle calculated in a load model block. The Q-axis or torque component is used to correct the load model and via this mechanism provide active motor damping. The D-axis or flux component is used in the feed-forward block mainly to correct the D-axis current errors. When the motor is rotating, the load model adjustment mechanism, together with the interaction of the back EMF and the motor voltage, causes the rotor to lock into the controller rotor position. At zero speed, where no back EMF is present, the D-axis command current is increased to keep the rotor locked in position, similar to the holding current applied with a stepper motor controller. Unlike a stepper motor controller, the Q-axis current feedback to the load block provides rotor damping at zero speed, ensuring the motor operates with the same dynamics at zero speed and at high speed. The test setup is shown here. It consists of the hybrid stepper motor under test coupled to a DC motor which is used as a load. 2 meters showing torque and speed are shown. The stepper motor is driven by a purpose-built motor control board, which is the upper board shown here. It has a motor control microcontroller using an ARM Cortex processing unit, a PWM stepper motor driver integrated circuit, plus support circuitry. The lower board is a 4-channel isolated digital to analog converter board, which has been added to monitor control variables in real time. The motor shown here, together with a table of parameters, has a holding torque of 0.44 Newton meters at a rated current of 1.7 amps. The controller is supplied with 24 volt DC. Attached to the motor for testing is a 5000 pulse incremental encoder. This is used to measure the actual rotor position for comparison with the position determined by the sensorless controller. The encoder output is sent to the controller board to allow this comparison to be made. The DC motor is loaded with a constant current source, the circuit of which is shown here. This allows a constant torque load to be applied at all speeds, which can be quickly turned on and off. The first test of the drive is a simple no-load acceleration to 1000 RPM, reverse and stop. Note that smooth acceleration is easily achieved at all speeds. The upper digital meter shown reads the approximate motor speed, with 1000 RPM corresponding to about 1 volt. The lower digital meter reads the load current applied to the DC motor, with 0.7 amps corresponding to 0.2 Newton meters. This remains 0 in this test. This test shows the response to a step load at zero speed. The D-axis current is set to 1.5 amp to hold the rotor steady. A step torque of 0.2 Newton meters is applied, causing the rotor to shift by 0.6 degrees, which is 30 electrical degrees. This is the plot of the phase error in electrical degrees between the encoder measured rotor phase and the rotor phase set by the controller recorded in the previous run. The rotor settles to its new position in the fastest possible time with good damping and minimal overshoot. Unlike normal servo motor drives, there is no jitter at zero speed. This makes the controller ideal for use in applications where the rotor must be held steady when stopped. In this test, the motor is accelerated to 500 RPM with no load. The rate of acceleration is set very high, requiring an acceleration torque of 0.2 Newton meters. The resulting plots are shown here. The graphs show the speed, the D and Q axis currents, and the rotor phase error. The speed shown in this and other plots is the controller's estimate of the rotor speed. It includes controller noise generated mainly by motor electrical nonlinearities, which is not present in the actual rotor speed. As the motor speeds up, the D-axis holding current is reduced to zero and it is no longer needed to hold the rotor in position. The interaction of the motor back EMF does this naturally. The acceleration torque of 0.2 Newton meters results in a Q-axis current of 0.75 amps as shown in the plot. Note that the rotor phase error stays close to zero electrical degrees at all times. Next, a step load of 0.2 Newton meters is applied at 500 RPM and the results plotted. As can be seen in the plots, the Q-axis current quickly rises to match the load. Speed droop is minimal. There is initial phase error, but this is quickly corrected. The next test shows full load acceleration with an 0.2 Newton meter load applied all the time. The plot shows the phase error is initially at 30 degrees as expected, but as the motor speeds up, the controller picks up the load error and adjusts the load model, bringing the phase error to zero, with the resulting Q-axis current rising to balance the load. These plots show the result of acceleration to 500 RPM with the very high load of 0.32 Newton meters. The acceleration rate is reduced to get the motor away. The phase error plot shows a very high initial phase error, but the controller is still able to pull this back to near zero as the motor speed rises. Built into the controller is automatic adjustment of the D-axis current above base speed to provide flux weakening, allowing operation at speeds well above base speed. The following test shows acceleration to 3000 RPM with the results plotted. As seen in the plots, a negative D-axis current is automatically applied above the base speed of 800 RPM to keep the peak stator voltage just below the available 24 volt DC of the control supply. The 24 volt limit also requires the torque limit to be reduced as the speed is increased, limiting the rate of acceleration. Now a load of 0.2 Newton meters is applied at 3000 RPM. The drive goes into torque limit and the speed drips to the point where the available torque matches the load torque. The speed drip can be seen in the resulting plots. Of interest is the plot shown here of the actual current for one motor phase and the current recorded by the controller at 3000 RPM. Also shown is the modulation level fed to the PWM modulator for that phase and the resulting motor voltage. The PWM frequency and the controller sample rate is 25 kHz, giving a sample period of 40 microseconds. This results in the current being sampled and the modulation levels being updated every 40 microseconds, which can be clearly seen in the plots. At 3000 RPM, the stator frequency is 2.5 kHz, resulting in one sample every 36 degrees. the feed-forward torque control algorithm can still maintain the phase error to less than 5 degrees even with this large sampling step. Here a pointer is attached which shows the rotor position with 1.8 degree increments marked. An 0.2 Newton-meter load is applied, causing a jump of 0.6 degrees. The rotor is then moved at 1 RPM for a short distance. Speed can be controlled very accurately and movement is smooth, with some variation due to cogging torque and motor nonlinearities. The next and final test shows operation with a position control loop and a position profiler added. The motor is moved 5 revolutions and back, first unloaded and then with an 0.2 Newton-meter load using a trapezoidal speed profile. Because of the quick response of the torque controller, position movement can be very fast. Feed-forward torque control was originally developed for the speed control of permanent magnet synchronous motors without the use of position sensors. Its performance in this role can be seen in another of my video presentations. Further details can be found on my website.